I am Professor Ravi Ramamurthy at the University of California, San Diego. I'm going to be speaking about light fields and view synthesis from sparse images, revisiting image-based rendering. Light fields enable a variety of interesting photographic effects, such as refocusing images after capture or enabling one to change the viewpoint. In recent years, a variety of different light-filled cameras have been developed. Lytro and Raytrix introduced commercial, consumer, and industrial light-filled cameras. Light also has a camera which can be viewed as a light-filled camera. Pelican Imaging introduced the notion that you can have an array of cameras on your smartphone. This has in fact inspired the modern development of smartphones, which often have 2, 3, or even 4 cameras with which you can do interesting photographic effects. Recently, with the interest of virtual reality, there have been a number of players in the industry that have developed virtual reality light-filled cameras. Notably, Google has a VR light-filled camera. What we would really seek to be able to accomplish is to take a few photographs of a scene like this with a simple mobile phone. These are just about 25 images captured casually with your mobile phone. And thereafter, you want to be able to create a light field that enables you to view it from different locations. Notice the reflections in the water change. Notice the highlights on this motorcycle. Once you're able to do something like this, you can view this in virtual reality. You can include it in computer graphics scenes with augmented reality, and a host of different applications opens up. These problems also relate to the older problems of image-based modeling and rendering. I'm going to show you a few slides from course notes on this topic more than 20 years ago by Paul Debevec and Leonard McMillan. Around the time I started my PhD studies, image-based rendering was the hottest topic in computer graphics. The feeling was the traditional computer graphics pipeline made modeling of realistic scenes very difficult. For example, for the bike, you have to model the geometry, you have to model the exact specular reflectance of the objects, and you have to be able to model the transparency of the puddles, etc., while rendering remains slow. Image-based modeling and rendering was an alternative where you start from source images. You may implicitly create some model, and ultimately, just by doing view synthesis, you create new images. The simplest example of that, courtesy of Leonard McMillan, was that you can take a single photograph, and if you have some notion of depth, you can warp this photograph as it would look from a new location to create a new 3D representation, or in other words, to be able to synthesize new views from different locations. However, this is not enough because you have to deal with occlusion and visibility issues. When you warp, there may be holes opened up which you didn't see in the original images. There might be multiple layers of the original images that go to the same pixel, and you have to resolve these occlusion relationships. Back in the mid-1990s, there was a group of people who felt that image-based rendering would completely overthrow the traditional computer graphics and, for that matter, computer vision pipeline. That hasn't quite happened. There have been some notable successes, such as the use of tourist photos to create phototourism and to create large-scale 3D models. However, the old image-based rendering never really worked as well as we would like. The reason for this is that occlusions and visibility are difficult. However, today we can revisit these problems because many things have changed. There is increasing interest in computational photography and light-filled cameras. There is a huge amount of interest in virtual reality. We have large images and even 3D datasets on which we can perform deep learning. And we have massive increases in processing power. Let me talk as a highlight about one of the projects we did that was published in SIGGRAPH 2019, where we see casual capture for light field synthesis. Here are 25 images which are on a grid, but they don't have to be perfectly regular. They're just captured with a handheld mobile phone. What we do is we take one of the images and we promote it to a light field. And so you can see that we have this light field ability of view synthesis here. And then we blend the nearby local light fields to create novel views. In this way, we have a method we refer to as local light field fusion, and it can produce these highly detailed and realistic light fields from a sparse set of images. We leverage Fourier theory to provide exact bounds on how much the sampling rate should be. What Fourier theory says is if you have d layers per view, so you have a multiplane or a layer depth image that separates the geometry into these d layers, then you actually need d square fewer views than you would get with a Nyquist sampling. So that's d fewer in each dimension. It's d square fewer views. And this means that you can get a dramatic reduction in the number of views needed. Moreover, using machine learning to infer these multiplane images or layer depth images, we see that up to about 64 planes, we can handle a disparity of 64 in terms of pixels or the shift in the shift or the disparity between adjacent views. And this shows that the machine learning pipeline actually gets us surprisingly close to a theoretical bound. This is another of the meta-level insights of this talk, to combine physically motivated ideas and sampling theory with methods from machine learning. We've applied this method to a number of different scenes with complex reflectance, complex occlusion, and we can produce light fields for all of these scenes from a sparse set of images. I now want to go back and go chronologically over the projects we've done in this area over the past 4 years. At SIGGRAPH Asia 2016, with my postdoc Nima Kalampari and my student Pingchun Wang, we considered the fundamental issue with light-field cameras is the resolution trade-off between spatial and angular resolution. In particular, in order to have the high angular resolution to get the properties of light fields, you need to trade off spatial resolution. Here you have an 8x8 array of cameras, which is effectively what the light field camera is, and effectively what the light-ray-illume camera is. But that means spatial resolution is reduced by a factor of 8 in each dimension. How can we keep the spatial resolution and in fact reduce the number of sub-cameras that you need? If we could start with sparse input views, in this case the 4 corner images in the light field. Now, if we do this, notice that you can actually get fairly large parallax shifts, fairly large occlusion between these 4 corner images. But what we seek to achieve is angular super-resolution, where you take these sparse input views and you synthesize new views between them. There is a straightforward solution in this era of deep learning, which is you simply model the entire process with a convolutional neural network. In this case, you take your 4 input images, you go through a convolutional neural network, you synthesize an output. Here is the result we get. And you see that for a single convolutional neural network, you get this kind of shower door effect, you get a number of artifacts. It doesn't quite look very realistic. In fact, this is in one way good for us. It shows that deep learning cannot be applied blindly. You actually need some human learning or human intelligence. In particular, we advocate a combination of physics-based architectures and deep learning, what we refer to as physically motivated deep learning. The high-level idea is to follow the pipeline of existing techniques, break the process into 2 components. The first of which will estimate the disparity and is a disparity estimator. Once you've estimated the disparity, you can warp or align the individual images, and then you can give this to a color predictor that produces the final result. However, you do not need to explicitly account for occlusion, which is a very difficult task. You don't need to explicitly account for specularities, because those will be modeled using learning, where each of the individual components is modeled using deep learning. Finally, you can train both models end-to-end simultaneously by only supervising on the final result. You do not need ground truth depth. Having done this, we produce results which actually have very good interpolation, that consider the occlusions, consider the parallax. If you go to our website or you look at our video, you can see many more examples where this simple idea is actually very effective. Of course, having gone to 4 input images, why not go all the way and try to reconstruct a light field from a single input image? This would enable remarkable capabilities where you can take your legacy photograph, promote it to a light field, view it in virtual reality, view it from different directions, refocus the image. In work with my PhD student Prathul Srinivasan and Ren Ng at ECCV 2017, we in fact showed a proof of concept that you could do this for a specific class of scenes, in this case scenes of flowers and plants. The leftmost image is a mobile phone capture. We actually recover 4D ray depths, and on the sides I'm showing the epipolar plane images corresponding to that, as well as the 4D light field. Then we can refocus images such as refocusing on the flower or refocusing on the background. And we show that it's also applicable to other classes. We have some examples with a class of toys. Here is the input single image. And from this, you can recover a 4D representation of depth that actually considers some occlusions and parallax. In many cases, is more accurate than methods specifically intended for light field depth. And you can output the local light field, which enables a highly realistic depiction of the appearance of this flower. Moving from images to video and going from angular super-resolution to temporal super-resolution, one of the challenges of light fields and light field cameras is that consumer light field cameras have limited bandwidth, and therefore they capture low frame rate videos. So the Lytro Illume is limited to capturing at 3 frames per second. It does capture a light field. You can see that this is 3 frames per second. It seems strobed, but you do have the 8x8 light field, and you have a nice light field you can get for it. It's just going to be at 3 frames per second. On the other hand, if you take a standard digital SLR camera, it can acquire this video at 30 frames per second, but only from one viewpoint. So the question is, can we combine the DSLR camera and the Lytro camera, which has 3 frames per second light field, to get a 30 frames per second light field? In fact, we were able to show that by combining these modalities, you can in fact obtain a 30 frames per second light field, where you can stop the video at any point to change your viewpoint. Moreover, you can refocus as the video plays or track the focus of a particular object. I would now like to close out this talk by discussing a couple of the papers that we have presented at ECCV this week. The first is on neural radiance fields, where we use a volumetric representation for view synthesis. But rather than having to recover the base voxels, we do this in a procedural way using a multi-layer perceptron. What this does is it tells you for any XYZ and viewing direction the volumetric density. And thereafter you can do volumetric ray marching to render the objects. We believe this use of volumetric representations is the greatest increase in photorealism. Moreover, the amount of data stored is very small. Actually, the network itself is only 5 megabytes because it is a procedural representation.
We present neural radiance fields, or NER, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation as a continuous function which is defined for any 5D coordinate, consisting of a location and view direction. We parameterize the scene representation as a fully connected deep network that takes in a single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We then use techniques from traditional volume rendering to composite these values along the camera array to render that pixel's color. Since the rendering process is fully differentiable, we are able to optimize the scene representation by minimizing the error of rendering all camera arrays through collection of standard RGB images. Our method is able to reconstruct high-quality novel views from a sparse set of input images of a scene. Our strategy outperforms prior work that also represents a scene within the weights of an MLP, as well as prior work that represents a scene as a set of multiplane images, or as a discrete voxel grid. Here, we visualize additional results across a wide variety of real-world scenes, each captured with 20 to 80 input images. Our neural radiance fields are able to render photorealistic novel views of scenes, with fine geometric details and realistic view-dependent effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network, requiring only 5 megabytes of storage for each scene. We can visualize the detailed view-dependent effects captured by our representation, such as the sharp reflections and specularities on this car, and the glossiness of this room's television and conference table. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusion effects in these tree leaves and ornaments.
Finally, we have talked throughout this talk about view synthesis, but ideally you would be able to also change the lighting in the scene and enable both viewpoint changes and lighting changes. In another paper at ECCV, we've taken a first step towards this, where again we recover a volumetric representation, and we do this with just mobile phone images with the light source being the flashlight and the viewer being co-located. Again, we determine a volumetric representation which can then be rendered to enable both lighting and viewpoint change.
We present a new rendering framework to reconstruct the appearance of complex real scenes for joint view synthesis and relighting. We apply a practical acquisition setup for this task and use a consumer mobile phone to capture multi-view images of the scene with flashlight. At the heart of our approach is the vertical-based volume representation that captures scene geometry and appearance. Each voxel in the volume consists of opacity, normal, and reflectance. We apply a differentiable rematching framework to render images and arbitrary viewpoints and lighting. During rendering, we trace a rate toward each pixel and accumulate colors along array. For each sampled point along array, we calculate its color using its reflectance and light information. To estimate such a volume, we start from an encoding vector and decode it into a 3D volume using 3D convolutional neural networks. We train the networks by minimizing the difference between the rendered image and the captured images and the collocated camera and light. And the learned volume can generalize to arbitrary novel viewpoints and lighting. Our method is able to reproduce the appearance of real-world objects and scenes with complex geometry, high-frequency tactile variations, and then Gaussian reflectance.
In conclusion, I have presented a number of methods for sparse reconstruction for view synthesis. These methods depend on the right kind of representations for the scene. We started by talking about multiplane images and layer depth images, local representations to create local light fields. And at this point, we have achieved the highest fidelity and photorealism with volumetric representations. In some cases, we can actually achieve theoretical bounds relating our results to planoptic or light field sampling theory, but in other cases we cannot, and it remains an open area of research. More broadly, I presented a framework of physically motivated deep learning where we use insights for physics, but then use learning to solve problems that are difficult in a physical sense. Moving forward, we want to go beyond view synthesis and also enable relighting. I just showed you some initial results there. There are challenges in terms of speed. Some of the inference for these models can take a very long time. And also the best results, such as in nerves or neural radiance fields, are achieved by specializing to a particular model. We wanted to be able to generalize these results to have a single network across all models. And we also would like to push in the limit towards single image solutions where you have just one image and you want to be able to create a light field. I showed an initial example of that, but are there general solutions? This also relates to an area known as inverse rendering, where you look at a single image and try to recover lighting, reflectance, geometry properties, which is also a complementary line of research that I have been interested in. Finally, I would like to acknowledge the students and postdocs who really did all of this work and came up with many of the ideas therein. And I would like to acknowledge my many collaborators on these projects, which would not have been possible without them, and the funding agencies. At this point, I'm happy to answer questions live. Thank you very much for coming to the talk and listening.